Today's separations class is all about batch distillation. Up until now, we have been analyzing continuous, steady state distillation. So given that most processes in industry are continuous, why would we ever want to analyze batch? And we want to motivate this by saying that sometimes a batch distillation can be advantageous for the following reasons. The first reason is that a batch process has very little or no startup time. So because the process is inherently unsteady, there is no waiting period for which you have to wait for the process to achieve steady state before you can begin taking product. In contrast, the continuous distillation column, as you'll see next semester in your unit ops class, there is a period which after you start up the distillation column that you cannot take product because the process is reaching steady state. And for this reason, batch processes are good for small or inconsistent processes where you're not making product continuously or 24/7. And the second reason is if you have a purity change over time. So this is good if you can sell products that are of varying purity. So say you're selling a chemical and you can sell 95% pure chemical at one price or 90% pure chemical at another price. A batch distillation is good because it's not a lot of work to change these specifications. You just simply change the amount of time that you perform the distillation. In contrast, for a continuous process, if you wanted to alter the purities of your distillate bottom products, you would have to alter a lot of things about the column, and then you would again have to wait that transient period for steady state conditions to occur again. So given these motivations, let's launch into the theory of batch distillation. And before I begin with that, I want to note a couple of things. Number one is that this is not covered in the Lane textbook. So if you're looking for a chapter on batch distillation, you will not find it in this textbook. I still think it's really important, which is why I choose to cover it. And the second thing is if you're looking online, single stage batch distillation is also known as the Rayleigh still. So some online resources you may find helpful, and you can look at that term as well. Single stage batch distillation is AKA the Rayleigh still. And that's what we'll talk about. We're going to start talking about single stage batch distillations, and then we will extend that analysis into multi-stage batch distillations. And this is named the Rayleigh still after the guy who did this analysis, Lord Rayleigh. He has a very funny picture on Wikipedia, by the way, if you look him up. Anyway. We'll start with drawing the process flow diagram, a typical PFD for batch distillation. The way I draw it is I draw a box, and in this box we have some liquid. This is where the feed goes. So this box we call, this is the reboiler, AKA pot or AKA still. So you see all three of those words, all meaning the same thing. This is the bottom of the Rayleigh still. All right, so we've got some liquid in here. And then the Rayleigh still just consists of a pipe. So this is also heated, by the way. So we have a heating coil in the bottom supplying some amount Q. And over time, this stuff is vaporizing through this pipe. And it is going to a condenser. And it could be a total condenser or a partial condenser again. Typically, you wouldn't see a partial condenser for a single stage Rayleigh still, just because there's no reflux notice. This is called the overhead product. And just like the distillation column, don't think that because I drew this thing floating up in the air that that's actually how it works. In real life, both of these things would be on the ground. It just helps me to visualize it that way. Right, okay, so at the beginning of the process, the overhead product is empty and all of the feed is charged or fed initially to the reboiler. So this is an unsteady state process, like I said, inherently. So the types of material balances that we're going to do is a little bit different. We need some more terminology here. I'm going to call the amount of moles at any time in the reboiler is going to have the letter B as its variable. So amount in the reboiler is going to be called B for bottoms. And this is in units of moles. And the composition at any time in the reboiler is going to be XB. So similar to before, right? We're only keeping track of the more volatile component. We're also back to binary feeds, by the way. So there's only two components. So we only have to take into account one of the compositions because the other composition is set with the physical constraint. In the overhead product, we'll call the amount there is equal to D. That's also in moles, and composition is XD. And the thing that changes from continuous to batch is that all of these are all functions of time. So D of T, XD of T, B of T, and XB of T. In other words, none of these variables are constant. So we might talk about at the end of the run, B is a certain value or D is a certain value, but as this charge is boiling, all these variables are going to be changing with time. So because of that, we need some initial condition. That's a big part of doing a batch process. You have to know how it starts. So just like in continuous distillation, we typically know what we start with. And for Rayleigh-Seal analysis, I'm going to call B at time is equal to 0. So just be super clear about that. B at time is equal to 0 is called F for the feed amount. And XB at time is equal to 0, we will call Z. Or XF. I have to share with you that sometimes I mix these up. I've used different textbooks over the years, so my notes have different notation in them. Z and XF are going to be equivalent. None of them mean anything else. So sometimes I like to use XF just because it's more consistent with XD and XB. It's the same format, but Z is what we use for continuous. Although I don't necessarily think it's a bad thing to use different variable names for batch versus continuous because they do signify different things after all. So the fact that I use different variables sometimes should hammer home the fact that these are different in general. And once again, I've said this previously, but I just want to hammer home this point again that D and B and F are all in terms of moles, not moles per time. So these are not flow rates. These are overall amounts. Two more variables that I have to fill in. As this charge is boiling, I have a constant stream of vapor that is going from the reboiler up through this pipe into the condenser and then finally to the overhead product. Call that flow rate V dot. So this is flow rate of vapor. This one is indeed in moles per time. So this is flow of vapor. And the composition of this vapor flow I'm going to call Y. So this is the mole fraction of more volatile component in the boil up. That's another word for the vapor going up. And just like all the other variables, Y is a function of time, but we can assume that V dot is constant with time. And that's going to simplify the analysis greatly. If you cannot assume that V is constant, then it'll be a little bit more complicated. So what type of analysis can we do for batch distillations? Just like before, we have a material balance, an overall material balance, and a component A material balance. Right, but it's not a differential material balance. This time it's an integral material balance. In other words, it's not in is equal to out. It is that final is equal to initial, or amount at any time t is equal to what was in at the very beginning. So we can write F, that is the total amount that is in the reboiler at time 0, must be equal to D plus B. So once again, same form as the continuous formula, but it means different things. So this means that F, whatever is in the reboiler at time 0, is equal to B, the amount that is in the reboiler at any time, plus D. And maybe it may help to just write D of T and B of T, once again, to clarify that this is a different in general material balance. I can also write a component A material balance of the same form, which is equal to XF times F, or Z times F. Remember, I'm going to use the same, use two variables to mean this, not on purpose, but sometimes they'll interchange, is equal to XD times D plus XB times B, where all four variables on the right-hand side are functions of time. Now notice that if we assume, like before, that x, f, and f are both known, so we know what's going into the Rayleigh still at time 0, then we have 4 unknown variables. And if we use these two equations as I've just given, then we have 4 unknowns minus 2 variables. And typically when you're doing a Rayleigh still problem, you'll have a design specification. So you would specify that you want the composition of the overhead product to be a certain thing, or that you want a certain amount. So given that we have 4 unknowns minus 2 equations minus 1 specification usually, that means we still have one other equation that we need to derive. So once again, assuming that we have a problem with 3 unknowns, so that would be whichever 3 out of the 4 variables between x, d, d, x, b, and b are not known, we have 2 equations, 2 material balances to relate them, but we need another relationship in order to relate these 3 variables to each other. And that relationship is going to be called the Rayleigh equation, and that will be the subject of my next video. So this was just the introduction, some terminology, the process flow diagram. Talk about the Rayleigh equation in the next video. See you there.